Hello everyone, welcome to AJJ Engineer. Today I would like to discuss with you about Mould Feed System, which comes under mold technology. Plastic melt from machine nozzle enters the cavity through sprue, runner and gate. This passage is named as the feed system. Sprue. In single cavity mold, generally sprue enters directly into the cavity. The diameter of the sprue at the entry of the cavity should be approximately twice the thickness of the part. The diameter at the nozzle end is fixed. Large sprue diameter increases cycle time, whereas small diameter causes excessive friction. The sprue surface is highly polished and draft of 11 by 2 to 21 bar 2 degree is given for easy removal. The starting diameter is made 0.8 mm smaller than nozzle size, and also a radius seating is given to avoid any misalignment. Runner. The runner is a channel machined into the mold plate to connect the sprue with the entrance to the impression. In the basic two-plate mold, the runner is positioned on the parting surface in a standard sprue. So the length of the sprue determines the opening at the cavity. The wall of the runner channel must be smooth and should not offer much restriction to flow. Sufficient draft should be given so that the runner sticking is avoided. The runner channel must be polished in line of draw to reduce pressure loss due to friction. Other factors that need consideration are 1. The shape of the cross section of the runner, 2. The size of the runner, and 3. The runner layout. In this picture we can see that this is gate length, gate, sprue, branch runner, runner and molding. Runner cross section shapes. The following cross sectional shapes are usually used: 1 fully round, 2 trapezoidal and 3 modified trapezoidal. The reason why these shapes are preferred are as follows. The runner should provide a maximum cross-sectional area for the pressure transfer perspective and a minimum contact area from heat transfer perspective. The ratio of cross-sectional area to periphery will show the efficiency of the runner design. The higher the value of the better the efficiency. Round runner has the maximum cross-sectional area and minimum surface area and hence the most efficient runner. Efficiency of various runner profiles. Round has got 0.25D, square also got 0.25D, semicircular got 0.153D. A square section is modified to trapezoidal section by providing a 10 to 15 degree angle on the runner wall. When the plastic melt passes through the sprue, runner and gate, the outer surface layer which comes in contact with the cold mold surface becomes solid. The material which flows will pass through the center of this solidified layer, and this layer acts as insulation and maintain the temperature of the central region. Therefore, the gate should be positioned in line with the center of the runner to receive the material from central flow stream. This condition is achieved with the fully round runner. The trapezoidal design is not a satisfactory since the gate cannot be positioned in line with the central flow of stream. The choice of runner section depends on the positive ejection of the runner system. A fully round runner is preferred for simple two-plate mold with flat parting surface. For molds with complex parting surfaces, the semicircular channels of the round runner can be used. For multi-plate molds, the trapezoidal section should be used for easy runner ejection. Runner size. Runner section that are too small require more injection pressure and more filling time. Larger runner gives better finish on the parts and minimize well line, flow lines, sink marks and internal stresses. Very large runners should be avoided. The following factors are to be considered when deciding on the runner size. 1. The wall section and volume of the molding. 2. The distance of the pressure from the main runner or sprue. 3. Runner cooling consideration. The cross section area of the runner must be enough to permit the melt to pass through the fill the impression before the runner solidifies. Runner length should be made as short as possible. It is undesirable to make a runner size more than diameter mm. However, for material with higher viscosity, the runner size can be up to diameter 12. Example, rigid PVC and acrylic. Large runner should be avoided for the following reasons. 1. Resistance to flow is more. 2. Cooling time required is more. 3. Wastage in terms of material, power and labor. 4. Clamping pressure required is more. Balancing of runners and arrangement of cavities. The following list the basic consideration in selecting the layout of cavities and the geometry of runners to distribute the plastic to all gates. Balancing ensures virtually equal flow of plastic through each gate of multi-cavity mold and or through each gate if there is more than one into each cavity. The plastic should arrive at all gates with same pressure and temperature so that all products within one mold have uniform characteristics. Virtually equal in this situation means it should be within reasonable limits. The runner length from each gate to the center of the sprue should be same. A balanced supply ensures that any change made in one of the parameters will affect all the cavities in the same way. Symmetric layout will ensure uniform cavity pressure, water line, screw hole position, etc. In general, balancing is recommended for all mold, but the need for perfect balancing has to be studied very carefully. Multi-cavity hot runner molds for consumer products and cold runner molds when injected with high pressure need not be perfectly balanced. Where a multi-cavity mold with interchangeable inside mold should be perfectly balanced. A balanced runner layout is not possible for a family mold. To attain balancing, there are several lines of thought. For many years, it is preferred to arrange the runner symmetrically from the point of entry of plastic all the way to each gate. While this is fairly easy with some layouts, especially with a smaller number of cavities, it is become difficult with large number of cavities. On the other hand, even though the geometry is symmetrical, the desired balanced flow may not be achieved because the flow of plastic through the channel change at every point of divisions into branch channels and depends on the amount redirection of plastics at the point of change. The flow depends on the accuracy of machining and the finish inside the channel. There may be temperature difference within the runner due to uneven heating and cooling of steel surrounding the runners. There are machining tolerance of the gates. Some resins are flow sensitive. Example, various layout are given below. Single cavity mold layouts, double cavity layouts, 3 cavity mold layouts, 4 cavity mold layouts, 6 cavity runner layout, 8 cavity runner layout, 16 cavity runner layout, 24 cavity runner layout, 32 cavity runner layout. Gate. The gate is defined as a passage through which the material enters the impression. It has a small cross-sectional area when compared with the rest of the feed system. This small cross-sectional area is required for the following reason. 1. The gate solidifies soon after the impression is filled so that the injection nozzle can be withdrawn for preparing the material for the next shot. 2. It prevents material coming out of the cavity once the plunger is withdrawn. 3. It allows for simple separation of the part from the runner, and with some gate this can be made automatic. 4. After separation it leaves only a small witness mark. 5. Better control on the filling of multi-impression can be achieved. 6. The reduced cross-sectional area increases velocity and so the friction which raises the temperature of the melt. 7. Gate sigmas can be avoided. 8. Better material shearing can be achieved. Requirement for a gate. The requirement of a gate are contradictory. Larger gates are required for fast filling and to reduce the stress in the part, but it requires more cooling time and leaves bad witness mark. A properly designed gate should meet the following requirements. 1. Should freeze after filling. Should permit unrestricted flow. 3. Should provide correct shearing conditions. 4. Should hide or disperse cold slug. 5. Should completely fill the part. 6. Should prevent jetting effect. 7. Should avoid deformation of the part. 8. Should not degrade the resin. 9. Should not freeze prematurely. 10. Should not leave bad witness mark. 11. Should not produce high stress in the part. Should not create blemishes. Specific gate design consideration. The following factors must be considered while designing a specific gate. 1. Short size of the part. Part material. Viscosity of the material. Any fillers. Glass, minerals, etc. Glass fibers. Flame retardant. Colorants. Appearance and function of the part. Wall thickness of the part. Longest flow length of the part. Molecular orientation of the part. Required cycle time. Position of gate. When designing an injection mold, the size and position of the gate is one of the most important consideration for correct molding of the part. Incorrect gate position can cause uneven filling, overpacking and dimensional instability. The position of the gate should be such that there is an even flow of melt in the impression so that it fills uniformly and advancing melt front spread out reaches the various impressions extremity at the same time. In this way, two or more advancing front can meet to form a well line with inherent mechanical weakness and surface blemishness in the molding. A central gating at the apex is done for slender core like components such as pen caps. A side gating in this case can cause deflection of the core. This is because side gating gives rise to a more rapid flow of material down one side of the impression, resulting in differently pressure which can move the core out of position. This also results in a thicker wall section one side, thus adding another weakness to that of weld line. So the following points should be considered while positioning the gate. 1. Try to avoid weld line. If it cannot be avoided, shift the weld line from the functional area. 2. Injection should not be directed to a slender core. 3. The material coming out of gate should immediately meet a restriction to avoid jetting effect. 4. Should ensure proper grain direction. 5. Should position at thickest portion of the mid part. 6. Should not affect the function and aesthetic of the part. Should be placed in a less objectionable portion. 7. Should not leave weak steel section. 8. Gate removal should be easy. 9. Hot runner gate required a necessary minimum distance between gates because of the physical dimension of the hot runner component. 10. In live hinges, gate should be located in the larger portion of the smaller portion should be filled to the hinge. The gate is sometimes positioned where it is less noticeable, hidden in a textured matte finish surface or in an enclosed portion. Balanced gate. When it is not possible to fully balance the runner system, it is done by balancing the gates. Balancing the gate can be done in two ways. 1. By modifying the land length and by changing the cross-sectional area of the gate. Position of gate. Jetting will be happening with the first one. The second image shows the smooth advancing of material. Position of gate for a pen cap. It's better always keep at the center portion instead of on the side to avoid core deflection. Types of gate. Types of gate must be carefully chosen to obtain the optimum filling conditions. The types of gates commonly used are screw gate, edge gate, overlap gate, tap gate, fan gate, diaphragm gate, ring gate, film gate, subsurface gate, valve gate, and hot sprue gate. Sprue gate. When the cavity is filled directly from a sprue or secondary sprue, the feed section is termed as sprue gate. The main disadvantage with this type of gate is that it leaves a larger gate mark on the component. Rectangular edge gate. This is a general purpose gate and it is a rectangular channel machined in one mold plate to connect the runner to the impression. Its advantages are the cross section form is simple and it is easy to machine. 2. Close accuracy in the gate dimension can be maintained. 3. It is easy to alter the gate dimension. All general materials can be molded through this type of gates. The main disadvantage with this gate is it leaves bad witness mark on the component. The following practical formula can be used for calculating the gate depth. D is equal to KT, where D is the depth of the gate, T is the wall section thickness, K is material constant. Modified rectangular gate. Fan. This is another type of edge gate but does not have a constant width and depth. The fan shape spreads the flow of the melt as it enters the impression and a more uniform filling is obtained with less flow marks and surface blemishes. This type of gate can be used with all conventional molding material apart from certain grade of rigid PVC. Overlap gate. This is a variation on the basic rectangular type of gate. Possible jetting by using a rectangular gate is avoided by this gate. For box type component, this type of gate can be used. Tap gate. This is a particular jetting technique for feeding solid block type components. A projection on tab is molded on the side of the component. Diaphragm gate. This gate is used for a single impression tubular shaped component on two plate mold. The part is gated around the part from inside. It can be seen as circumferential fan gate. This gate is usually 0.1 to 0.15 mm depth tapered towards the sprue. The advantage of this type of gating are 1. The part will remain round. 2. No weld line. 3. No deflection of the core. 4. No distortion of the part. 5. Fast filling. The gate can be connected to the sprue with a disc or a runner. The runner design is preferred to so disc especially for larger components because of less wastage. Ring gate. The function of this gate is similar to that of diaphragm gate. This type of gate is used for tubular type moldings when more than one impression is required in a simple two-plate mold. The gate provides for a feed all around the external periphery of the molding and permits the use of conventional runner system. Film gate. This is a long rectangular type edge type and it is used for larger thin wall components to assist in the production of warpage free products. Pin gate. This is a circular gate used for feeding into a base of the component and it is preferred to the through gate because it is smaller in diameter. Subsurface gate. The subsurface gate is a circular or oval gate which submerges and feeds into the impression below the parting surface of the mold. It is given in two-plate mold, provides automatic separation of the gate. This gate is sometimes called as submerged gate, submarine gate or tunnel gate. Advantage of subgates are 1. The foam being on one mold plate has no matching problems and precise dimension can be achieved. 2. If the more oval foam is used, the filling rate of the impression can be controlled independently of the gate seal time. 3. The gate is sheared from the component during the ejection. Degating is automatic. 4. Leaves very small witness mark. 5. Gating can be on the sidewall. Size of subsurface gates. Recommended diameter for subsurface gates are given below. Curved tunnel gate or winkle gate. This type of gating may be selected when gating on the sidewall is unacceptable. The gate length in this case is comparatively long. The gate extending from the runner should be progressively reduced to meet the impression. Enough space should be provided between the ejector pin and the gate so that material in the tunnel deforms and comes out. This method is applicable only soft and flexible materials. The tunnel shape is obtained with a lock insert. Valve gate. Valve systems are two types. Automatic shut-off valves, that is spring actuation. 2. Externally operated shut-off valve, mechanic, hydraulic or pneumatic actuation. The principle of valve gating is that the closing or opening of the gate is independently controlled. The spring-loaded pins, the valve opens at the beginning of the injection pressure. Pneumatically, hydraulically or mechanically actuated pins, the opening or closing is independent of injection pressure. The injection unit can withdraw immediately after injection, but in all the cases, holding pressure is not required. In earlier design of valve pins, a plain cylindrical pin was used. The problem with this straight pin are poor alignment, deflection of the pin, wear of the gate and valve pin breakage. A tapered pin end avoids some of the problems of straight pin, but the gate must be stronger to withstand the force of pin shut-off. A stop inside the valve bushing should limit the valve pin stroke to prevent excessive load on the gate. In both the case, allowance or heat expansion should be considered. Automatic valve gate. The automatic shut-off valve is based on the spring-loaded system. When the injection pressure builds up to the shutting of the spring, the pin moves away, allowing the material to enter the cavity. When the pressure is reduced, the pin comes back and closes the gate. externally operated valve gate. The principle of operation of this system is the pin is attached to external actuating device. The valve pin has two positions, either open or closed. The pin is generally actuated either by pneumatic or hydraulic system. Mechanical systems or combination with other type is also available. Mechanically controlled pin can have single or double acting operation. One single act. The pin moves up as the pressure in the system builds up. The pin is moved down a spring which acts as the pressure in the system drops. An inline air cylinder or wedges which act when the pressure drops. Two double acting. The pin is moved up or down by inline pneumatic or hydraulic cylinders operated at any required time. The gate is open at the beginning of the injection pressure. Sprue sizes. Sprue sizes for polystyrene depending of the mold weight are given below. For other materials, the sprue diameter should be multiplied by the following factors. Hot runner gate. A hot runner system maintains a molten flow of plastic from the molding machine to the gate. This gate is open for the flow of material under pressure, but when the injection is over, the gate solidifies and closes the gate. The material beyond the gate area is always hot. The solidified material in the gate prevents the melt coming out of the run. When the mold opens, the material in the gate goes along with the part and the remaining material stays in the gate as act as a plug. So in hot runner gated mold, there is no runner ejector every time the mold opens. At the next cycle, the material in the gate is pushed into the cavity and the gate is again open for injecting material. The plug which is pushed into the cavity usually melts the mixes with the other material. Hot gate types. Through wall gate, circular gate. Through hole type are for direct part gating or feeding runner profiles. The cost of this gate is less. This type can be used where some gate wastage and a circular mark is allowed. The advantage of circular gates are they can be small, they are well suited for heat sensitive material, they are very cheap, they are easy to operate. The disadvantages are the injection pressure may lift the steel around the gate, difficult to control the heat flowing away from the gate, premature freeze of gate, more rolling occurs, bigger gate wastage compared to the other hot gates, point gate or annular gate. This type gate was primarily designed for single cavity mold with direct jetting. Its sharp pinpoint torpedo tip leaves on the part only a small witness mark, about 1/3 in height of the gate diameter. Since the opening within the gate creates an annular opening, the plastic enters the cavity like a extruded tube. It gives excellent cosmetic appearance of the gating and also prevent premature gate freezing off. There are two types of chamber available, namely closed chamber and open chamber. Closed chamber is within the hot sprue bush and open chamber is formed outside the tip with the opening made in the cavity. The closed ring chamber is recommended when a circular witness mark is acceptable on the component. The open chamber is used when no witness ring is allowed on the component. It is also recommended on ribs and curved surfaces. The advantage of point gate are frozen gates rarely occur, less straining occurs, ideal gate easily straining material like PS, smaller wastage than circular gates, larger cross section can be created by only little increase of the gate opening. The disadvantage of point gates are if divergent streams coming out of the center of the nozzle are not properly mixed during the passage around the gate, flow lines will result. Point gating is not suitable for all materials because of the high pressure required to flow the material through the narrow gap. The narrow gap may be filled with dirt, not suitable for heat sensitive materials as material may degrade due to long exposure to heat. Edge gate. The principle is same as circular gate. At the end of the injection cycle, the gate solidifies. When the mold opens, the gate is sheared leaf slug within the narrow space between the cavity and the hot plastic in the runner system. The slug prevents the melt from drooling into the cavity. When next shot happens, the slug pushes into the cavity. Valve gate. Valve gate is mainly used for large shear sensitive material where low pressure filling is required. The main advantage is that the material in the gate area can be pre-compressed and the material can be injected with high force and in large volume. There is no restriction for the diameter. The valve pin can be operated mechanically, hydraulically or pneumatically. Axial gate, multiple gate nozzle. The multiple gate nozzles are suitable for multiple gating of small parts in multiple cavity mold or larger parts in single cavity mold, providing up to 6 points for screwless injection. Located on a small circle, this self-contained manifold with probe gating offers optimum gate cosmetics. Both circular and pinpoint gates are available. Runner diameter calculations. To calculate runner diameter, the following formula can be used. Here the material and typical runner diameter used for that. PVC, plasticized. Long runners require increased diameter. All main runners in a mold should be of equal diameter. Diameter of all of the secondary runners should be at least 0.7 mm less than the diameter of the main runner. Mass of runner system for material density 1 gram per centimeter cube. Diameter of runner based on the mass and also the trapezoidal runner. Mass of the runner for the other material can be obtained by multiplying the above values by the relative density of the particular material. Gate calculation. When deciding on a specific gate design, the following factors must be considered. Short size of the part, material to be molded, viscosity, additives, glass fibers, flame retardant, cosmetic appearance of the part, thickness of the part wall, longest flow path of the part when designed. When are probably the most ignored and mistreated part of the mold. Yet, when can do more to lower injection pressure, reduce cycle time, eliminate stresses, burn marks, and minimize the warp and shrinkage than any other single element in the mold construction. When allows tepid air to build up gas by resin melting to escape from the closed and sealed mold into which molten plastics is injected. If the air is trapped inside, it will result in a short filling and sink marks. The table below lists the recommended vent depth for runner and cavity for different materials. Consider lower value for easy filling area and higher value for different filling area. It is just as important to vent the runner as it is for cavity. Normally the runner is vented to twice the depth of the cavity because it is not a problem if there is little flush on the runner. In fact, flush is an indication of proper venting. Venting should be equal to 30% of the part perimeter. If the runner is vented by only 20% of the parting, only need to be vented. Vent should be placed equal on both sides of the length of the runner and cavity. Vent width can be from 6 mm to 12 mm. It can be made less than 6 mm for small part but never more than 12 mm as the material may sink in close the vent. It is also necessary to relieve the vent leaving a land of 3 to 5 mm. The relief depth is made to 0.1 mm. As far as possible, the vent should be ground. Rules for venting. 1. Vent to suit the anticipated flow of material. Vent at the closed end of all pockets. If the pocket machined from solid, vent pin must be provided at the deepest location. Whenever possible, provide moving vent pins. Vent should be as deep as possible without all rib bottom should be vented. Every vent must lead to outside. Wall thickness. The below table gives a guideline for common materials wall thickness, which gives minimum and maximum.